Okay, today's video is from page 142 in the textbook. It's chapter 4.2. It's a discussion about critical points and local mins and local maxes and sort of an analysis of all the different points and the extreme points on that we can have on a function. So it starts off with a couple of definitions, where local max or maximum points might occur and minimum points might occur. We've seen these definitions before. We're starting to also consider mins and maxes and local mins and maxes as cusp points or corner points. They can also be stationary points. We're used to seeing stationary points on continuous functions. Okay, but we've got to also talk about cusp points. One good example today is going to turn up as a cusp point, the corner points, and then also these infinite slope points in situations where we're looking at not only the point, but the derivative around the point, the slope of the tangent line around the point, and noticing just how things are changing here. In each of these situations, we've got slope of a tangent on the left part of the point, okay, as increasing, and then on the right part of the point decreasing. When it's a minimum point, it's decreasing, then increasing, okay, and down here, it's decreasing and then continuing to decrease, but these are in fact called turning points or inflection points we're going to see. Okay, they're also called in advanced functions. You may have heard them as turning points here. And then these are situations where they're important points. Certainly something's happening. There's a change in direction of the point, but the slope doesn't in fact change. The slope of the tangent is increasing and then continues to increase. These other situations up here, okay, have slopes that change where the turning point or the extreme point changes here. Okay, so let's do a real quick, okay, classification of some points here. Now I'm going to pause this tape like I did last time and get some of my answers up here on the smart board or the file, and we'll take a look at all these points. Okay, so we've got critical points at the following, each of the following points, A, B, C, D, E, and F. Okay, so I've labeled them, and we're going to talk specifically about them, what they are, and again, this is something you guys have done in the past, and then we're going to talk about the slopes and maybe classify them even further a little bit. So at point A, x equals -5, we've got a situation where we've got a local, right, a local minimum, okay, and it also looks like it's a bit of a cusp point, right? Okay, at B, x equals -1, we've got another, maybe more of a corner point this time. We've certainly got a global, and we also call those absolute, okay, cusp, corner. Not too particularly concerned about the difference between cusp and corner points. C, I've got a local min as well, right? And that's would be a corner point. Okay. D, okay. Maximum, right? Local max. This is the absolute max of this. Okay, that would be a local max. Okay, that's a stationary point. Okay, E is a local max. Okay, we've got a cusp point. Okay, and F equals at F x equals 7. Okay, that's a local max. Okay, and I think that's just a stationary point, or really an end. It's an end point of my function or my domain. Okay. Now, slope of the tangent is the last thing. Okay, and this is why these are critical points here. Look at the slope of the tangent near A, and then it increases. So it's decreasing and then increasing. Okay, here it's it's positive, and it's increasing, and then it's decreasing. It's decreasing, then going to increasing, increasing, and then decreasing, decreasing, and then increasing, and so on and so on and so on. And that's the important part when you have to look at the slope of the tangent lines. Let's do our next one here. Okay, find the critical points. critical points always start with derivative. So the derivative I'm going to take first, set it equal to 0, and solve. I'm just going to pause this to let you guys work through the derivative, okay? And we'll be back in a minute. Okay, and hopefully you found the derivative. You've set it equals 0. You involve factoring and then just identifying a perfect square there. I have critical points at x equals 0 and x equals 3. Okay, next up I'm going to classify them a little bit, and I'm going to use a sign chart again, something we've done in the past in advanced functions and something we did in the last chapter. So again, I'm going to have you guys set up a sign chart, and I'll pause the video and join you again in a minute. Okay, I set up a sign chart, but I'm going to do something just slightly a little bit different here, trying to make it so that it includes all my information here. Okay, so now I've got, okay, a sign chart. I used all my proper intervals. Okay, x is less than 0, then x gets picked up from 0 to 3, and then there's a breakpoint at 3, another critical point we found, and then I need the interval, the last interval, where x is greater than 3. Actually, specific points in each of the intervals are chosen. X equals -1 I'm going to use, x equals 1 in the middle interval, and then x equals 4 in the in that third interval. Now I've also done something up here that's new. I've identified where I found my line or my table, okay, in this chart, this line that separates the two intervals. I'm going to call that line x equals 0 because that's exactly what's happening here on this red line now. Okay, and that's the point x equals 0. So this is the left of 0, this is the right of 0. Same thing with 3 here. 3 is the critical point. It approaches 3 from the left, and then it continues from the right of 3, and that's it. Now I'm also going to use, okay, trying to figure out the sign, okay, of this particular, okay, function here. But I'm going to write it as, okay, the one we used here, and that's the function I'm going to use to find the sign here. Now I just broke and factored it this way, but that's how I would have maybe continued to factor. Okay, so when x equals -1, I'm going to put -1 in here. That'll be a negative, and when I put -1 in here, that'll be a negative, but then I'm squaring. So I've got the product of, okay, a negative and a positive, which is a negative, and that's less than 0, so that's a decreasing interval. Okay, when x equals 1, I have a positive and another positive. It's always squared, so it's always positive, no matter what my value of x is in the x minus 3 quantity squared, it's always positive. So now I've got my derivative is a positive and a positive and a positive and a positive is always greater than 0. So that's an increasing interval. And I'm just going to clean that up slightly. Okay, and the next one, when x equals 4, that'll be a positive and a positive. So my derivative function is positive, positive. Two positives make a positive, and that's also increasing. Okay, so we got it? We straight? So you tell me at x equals 0, what is it? Okay, and at x equals 3, what type of point is this? And that's the question I'm asking. Okay, so if it's decreasing, and then it hitting 0, and then it's increasing, it looks like it's a minimum point, right? Okay, and because we know our original function is a quartic function, okay, and I know it opens up, right? This minimum point is actually going to be a global, okay, or an absolute. Okay, it's going to be the absolute minimum here. All right, and x equals 3, it's increasing, and then it's flattening out, so that at x equals 3, I've got a 0 slope, and then I continue to increase. This one would be an inflection point, okay, or we call them turning points. Okay, and there, I've classified my critical points by using a sign chart to represent the slope of the tangent line, okay, the derivative. Now I'm going to pause this and call this up in Desmos just to confirm my findings here. Okay, so here's the function in Desmos. Now, unfortunately, I concede my first minimum, but if I zoom in, Okay, 3 is way out here, and I can't see that, so I have to adjust the settings. You may know how to do this. I'm going to adjust my y-axis to about 100. Okay, and let's see if I have this. Yeah, there's my point at 3, and there's my other one as well too. So there's my global, okay, minimum, okay, and a turning point. It looks like it's bending here. Even if I adjusted this a little bit more, okay, okay, you can see it even better like that. Okay, so there we go. That's the situation we've got on our sign chart here. Okay, let's take a look at the next one. Okay, a little bit more of a challenging function here. Okay, so I want to find the critical points. We know the critical point is going to be, okay, when the derivative equals 0. Okay, so let's take this derivative 2/3 x plus 2 to the negative 1/3, and then times 1. I don't need that times 1 as a rational. Okay, I have this situation. Okay, so what is this function? What's it look like here? I don't want to graph it quite yet, but I've got, okay, some pieces of information here. Okay, so let's go back to the original function. It looks like I've got a, okay, when I've got an x-intercept here, when x equals -2, that -2 would be +2, that would be 0. So 0, okay, I've got a, here. Now what have I got at this situation here? What about when happens at -2, when I put this in? What happens to my derivative function at -2? Well, I've got -2 in the third root of 0. It would be undefined. Okay, so we've got at -2, the slope is undefined. Okay, that's a little bit strange. I actually have a point at -2, but I've got an undefined slope here. Okay, so I think maybe we need a bit of a sign chart here and sort of figure out what's happening here in and around -2. Now, -2 being undefined, okay, and also being a root, that can be on the sign chart here, but my sign chart is going to look like this. I'm going to look at points below -2, okay, and I'm going to look at points above -2. Okay, so when x is less than -2, and when x is, and I'm going to look at my derivative function. Okay, now another thing as I'm taking a look at this graph, do we have an idea of what the domain is? The original graph, okay, I can take the third root, okay, of any number. -2 is a bit of, well, -2 is not a problem, it's 0. But if it was less than -2, so -4, okay, I can still take the third root and then square it. Okay, it's going to be, okay, basically, it doesn't take you long to realize that our domain is here. Okay, x is an element of the real number system, but our range, okay, is always going to be greater than 0, right? Okay, and that's because this 2/3 exponent, I take the third root first. I can take the third root of a negative number, and then I square it. So I'm always going to have a positive value for y here, okay, no matter what my x is. Okay, so we're beginning to think we know what this maybe looks like. Let's figure out the sign. Now I need a value here. Let's use -3, and let's use 1 here. Okay, any value works in there. Okay, so what's the sign of my derivative function at -3? It looks like it's a negative third root. Third root of a negative is still a negative. It's going to be a negative. That's less than 0. So this is decreasing. Okay, so my function's decreasing, okay, at less than -2. And what's happening when x is 1 here? That would be a positive situation. And that's greater than 0, so that's increasing. Okay, so let's go to our graph. Do we have enough to graph it here? What do we think? Well, domain and the range. So anything works for x, but it has to be positive. So it has to be in this, okay, above the x-axis. Now I've got this situation. When I'm less than -2, okay, when I'm less than -2, I have decreasing function. At -2, it's undefined. The derivative function is undefined at -2. Okay, so that might be an infinite slope situation, maybe a cusp point at -2, and then it increases past and beyond -2. So here's what the function looks like actually. Okay. And okay, this is the undefined part of it here. I'm just going to put eraser, erase some of that. Okay. Now I think at any point, okay, you might need to solidify that. We might need some other values. Okay. So what's a value when x equals 0, let's say? Okay, so I might want to find some, okay, some just sort of test values. F at 0 certainly would be, okay, I might want to find an F at 1, and I might want to find sort of an F at -2, just some random points to help us fill that in. I don't want to use a full table of values. It's not a grade 9 class, but certainly a couple of test points to give us an idea of what this looks like. And again, you guys can confirm that in Desmos. I think I've done sort of that situation. While I'm here though, okay, it should be, okay, it should be sort of wise to talk about sort of some endpoints here. Okay, so we've got, okay, the limit as x approaches -infinity of my function goes to positive infinity. The limit as x approaches, okay, goes to infinity. And how about this limit as x approaches -2 from the left of my function? Okay, looks like I've got, okay, 0 on the top, and the limit as x approaches -2 from the right of my function. Okay, we approach 0 also from the top. Okay, and that's represented up here. Okay, let's move along and take a look at the last and final example here. I'm going to, okay, pause for a second and get this set up. Okay, before we get that set up, I just have my Desmos graph open here, and I just wanted to show you that last function. That's exactly what we've got here. Okay, next type of situation here. Let's go with this one, and that'll conclude the lesson, today's section in 4.2. Okay, so here we've got to come up with, okay, we've got a general form of a function. It's a degree 4 function. We've got ax to the power of 4 plus bx squared plus cx plus d. So there's no x to the power of 3 term. And I've got some information here. Local max at -6, okay, and a local minimum at 1 and -8. Okay, so this gives us a lot of information, okay? This gives us, okay, 2 points on the graph, okay, so I certainly can, okay, use these 2 points, and I know their local maximum, so the derivative of this function at this particular point, okay, happens to be 0. So we've actually got 4 pieces of information. We've got 2 points, okay, and we've got local max and local min information about this. Let's take the derivative though first. Okay, this would be 4ax to the power of 3 plus 2bx plus c. Okay, now let's put in some points here. Now I've got, okay, my original function, okay, has a point on it at, okay, 0, okay, and -6. Okay, so that means a 0 plus d 0 squared plus c 0 plus d equals -6. That'd be 0 plus 0 plus 0 plus d equals -6. Okay, so I've already solved for d. Now I'm going to pause and do it for the next one here, and okay, and basically what we're going to do here is plug in this point and see if you can get the resulting equation. Okay, my next resulting equation came from the point 1 and -8, and I substituted x equals 1 into my original function. let that equal -8. So I got an expression a plus b plus c plus d equals -8. I previously found that d was -6, so I substituted that in and collected my constant terms on the left hand, or sorry, the right hand side. I have an expression a plus b, okay, a plus b plus c equals -2. Okay, next thing I'm going to do is plug in this particular situation. Okay, this is gathered from the fact that I was told I have a local maximum at 0 and -6. So that means I use my derivative function, set x equal to 0, and the resulting f prime at 0 is equal to 0 here because it's a local maximum. So what is my derivative function here? 4ax to the power 3 plus 2bx plus c. Okay, so I'm going to, that's my f prime. Okay, I'm going to let all the occurrences of x be replaced with a 0, and I'm going to set that equal to 0. Now that means I've got 0 plus 0 plus c equals 0, so c equals 0. Okay, there's another solution here. So I really could, at any point, put 0 in here. Fine, I'm really getting to solve this here. I've already found d equals -6, c equals 0, and I have a plus b equals -2. I want to do it for the next one here. So I've got another point here. F prime of 1 also equals 0. Okay, so my resulting derivative function, when I replace x with 1, I found c to be 0. So I can just put that in temporarily. Okay, so I'm going to have 4a plus 2b, plus 0 equals 0. Here, 4a plus 2b equals 0. Okay, so I've got this equation, and then this one up here. Now I have to use these two equations and solve for a and b. Now that's pretty simple. You might remember this from grade 10. We've talked about this. Let's rearrange this one and solve for b in terms of a, and let's solve by substitution here. So let's take my second equation, 4a plus 2, but instead of b, I'm going to write in what I just rearranged, -a minus 2, that equals 0. So I've got 4a minus 2a minus 4 equals 0, 2a equals 4, a equals 2, and back substitution into my other one here. If a equals 2, b would equal -4. Okay, and let's just all bring it together. I've got all three of my variables here, so I'm going to say the function is, I think my first one was a I just found to be 2, so I'm going to write 2x to the power of 4. Then I had a b minus 4b, or sorry, let's try this again. 2x to the power of 4, and then minus 4x squared. I'm replacing my coefficients a, b, c, and d, with 0x, and then a minus 6. I'm replacing them with my actual values here. I'm just going to write this one again because I don't write 0x. That's my answer. Okay, I think this should be pretty self-explanatory. A couple of the homework questions involve doing this last example here, and then doing some basic polynomial functions so we can state critical points here. So good luck with this. Roll along here. For 4.3, I'm not going to do a video lesson. I'm going to leave that lesson optional. just in the spirit of keeping some things out of here. Let you guys look at that if you want to. It's a discussion about asymptotes, horizontal asymptotes, vertical asymptotes, and oblique asymptotes. And but again, I'm going to leave that optional, and we'll pick up a video lesson in 4.4. Thanks. Have a good day.